Hi, my name's Norm, Chief Technical Support Engineer at NI. And this is going to be the first of a series of discussions that we're going to have around complex data, or IQ data, as it's commonly referred to as, in terms of what is your IQ. And in this lesson in particular, we're going to talk about RF power. Now, complex data sets can describe a lot of different things. But very commonly, RF engineers and RF training starts off with one of the basic fundamentals of power. Now, a lot of us who have gone through any kind of engineering course understand the many ways that you can represent power in terms of volts squared over R, or volts times current, and a variety of different transforms. But in particular, in the RF space, we talk about power as commonly as reference to 1 milliwatt, or just in terms of watts in general. And for what we have here, we're going to go ahead and figure out, and by the end of this lesson, you really should be able to take an individual complex data sample, understand what it means with regards to the carrier as a minimum from power, and then go ahead and figure out how to transform that single sample of complex information and turn it into an understanding of what the carrier's power was during a short period of time. Now, the way that we're going to do that is we're going to go ahead and use our vector signal transceiver and an oscilloscope that you see here. And we're going to go ahead and pull open some LabVIEW diagrams and talk about how you can leverage math and features that are already built into the product and to very quickly take that complex data sample and turn it into a power value that you can trust. So without any further ado, let's go ahead and get into it.
So the system that we have set up, we have a 5644 vector signal transceiver. And out of that, we're just looking at that RF out port. We're just going to be generating a single tone, nothing special, nothing modulated for this experiment. And we're going immediately next to it, or to that module immediately next to it, which is that 5162. And that's just an oscilloscope. So anybody who's familiar with looking at just kind of a raw signal on an oscilloscope, we should be able to look at that carrier's raw representation sample per sample, or wave for wave, in channel 0 of that port. So one of the things that you can see here indeed is that we are generating a signal at 100 megahertz. So we know that the period of a 1 gigahertz signal is going to be 1 nanosecond, so 1 gig to 1 nano. It's 10 to the 9 to 10 to the negative 9. So one order of magnitude down of 100 megahertz. Of course, we're going to see a sinusoidal signal, but we should see a period of about 10 nanoseconds. So we've got 10 nanosecond period in there for every cycle of the carrier at a power of 0 dBm. Now 0 dBm indeed equals to 1 milliwatt. I apologize for the poor drawing here, but in particular, this is what we should see on our oscilloscope. Now, we haven't declared how much we should see on the voltage peak to peak, volts RMS, or anything like that, but we know that these two things should be true. So let's go ahead and we're opened up Instrument Studio, and now we're looking at that actual RF carrier itself. Now, it's unmodulated. If we were to look at it on a spectrum analyzer, it would just be a tone. But one thing that we can tell very specifically about this signal is indeed we have a signal that is approximately 0.32 volts, or 320 millivolts peak, or if we actually look down here in the bottom, it's about 640 millivolts peak to peak. And so that's all that we have. It's just a single tone signal. This is the carrier, and we can at least get the amplitude out of it. Now, there are other things that we might want with complex information, or just to know about the carrier, how the phase is, or the frequency, but we're going to leave that be. Those are going to be for future lessons. What we're going to talk about now is how to basically understand what the complex data value means in relation to the carrier at 0 dBm that we just saw. So one of the things that's particularly important is to note that a carrier, even in a situation like what we see here, where that carrier, in this case, the amplitude of the carrier is changing over time, that if you were to take a small enough slice, say, of that carrier, as we're showing here, actually this is even larger than what's being represented down here, and you were to blow up a really small slice, it no longer looks like a changing signal. It actually, for a small enough period of time, looks like many cycles of a just straight sinusoid, just like what we were seeing with the unmodulated carrier just a moment ago. And we know that one of the things that we can describe this signal is basically volts peak or volts peak to peak. Now, the reason that this is so important is because basically the relationship of volts peak or volts peak to peak is directly transformable back to power. And if you remember, I think if I were to move it over here, if I'm not mistaken, I think it was volts RMS squared over the resistance should give you the power in watts. So this is basically the math that I think all of us have learned at some point in time. If you have a sinusoidal signal, you can get the watts delivered based off of that. But we're only talking in terms of volts peak. So there needs to be a couple more steps in between to basically take a little bit of information that you might know about a carrier and then turn it back into watts. So I've been talking a lot basically about the carrier, volts peak to peak, but this is supposed to be a lesson about I and Q, right? Well, one thing that we can know is that when we actually have basically a signal, basically even a simple sinusoidal signal, we can represent two major things about that signal. We can represent the amplitude, I'll put here as alpha, and we can also represent the phase, I'll put here as theta. Sometimes vectors are basically drawn, we'll just call it, in this case, we'll just call it the beta vector. Can be described indeed of the magnitude of the beta vector, indeed, in this case, equals alpha. And of course, basically it can be drawn as beta equals alpha as theta in a couple different ways. Now, on a plot, whether you call it real, imaginary, or I and Q for in phase and quadrature, that basically comes out to be represented as an individual point on the complex plane, once again with alpha and theta. Now, the reason that I want to talk about I and Q in this manner is I want to break you. I want to melt your brain if you are hooked on thinking in terms of I and Q. Because if you constantly think about your I and Q as a representation of your carrier signal, you're going to miss out on, it's going to be a lot harder to understand a lot of things. However, if you think of your carrier, once again, I could think of this as I and Q of beta. But if I think about it as this alpha and theta, or actually probably better put, let's just talk about it in terms of how it's referred to in language as rho and theta, the Greek letter rho, then all of a sudden your data set, this complex data set, don't think about it as I and Q, think about it as complex data, or even an array of complex data. And then think about it as really an array of magnitude and theta as well. Because what ends up happening is very often in communications, you care a lot about the power of the signal. Well, information and knowledge of the power of the signal has nothing to do with the phase. It has everything to do about this value of rho and what rho means. So what does rho mean in the essence of a complex data set? Well, rho is once again relational to the size of that vector. The size of that vector, rho, is equivalent to volts peak over that period of time that you were seeing before. So if I were to talk about this signal that we're looking at down here, and I were to describe this complex signal, this carrier, and I wanted to talk about during a small enough instant in time where the carrier looks like it's not changing, that's kind of what happens when you zoom in close enough to it, we would say that the value that would come back out of that complex value would be a value of 500. Now let's just presume for a second this is in millivolts here. So it'd be 1/2 volt, and that's kind of what's being representative by this graph that we're seeing. So let's talk about that a little bit more. So now we started off with, I have a complex value. I'm used to thinking about it as I and Q, which can be a little, it's not that hard to understand. I mean, it's just the value on the axes, but we're going to throw that away. We're going to think about it in terms of magnitude and phase. No data is lost. It's just a different way of thinking about the data set. And then we're going to say, all right, that value of rho
is equivalent to volts peak of the carrier for a period of time. And so if we go back to our demo here, volts peak for our example was a value of, if I'm not mistaken, about 320. Right? And we were generating a 0 dBm signal. So let's prove this to ourselves. So we've got a volts peak of 0.32 volts approximately. And we know that this should be 0 dBm or also 1 milliwatt. Okay, so let's work through the math to figure out how we take this value of volts peak and eventually get back to how many milliwatts that volts peak get us. So we know a couple different things about power conversions. In particular, we know that when we're talking about things in the units of dBm, it is a logarithmic ratio of power to 1 milliwatt, and that's a very important distinction. And so let's just break the math down on this logarithmic math of basically we still have our 10 log P, and then of course 10 log 1 over a milliwatt. You take that reciprocal, and it's basically negation to 10 log of 1 milliwatt, which turns into, this is now relational to 1 watt, or just a value of 1. And so now this is just a value of 30. So now we've got 10 log of P times 30. Now, once again, we're not given power by our vector signal analyzer. We're given a complex value. So we need to get closer. We need to get to volts first. Well, some things that we know specifically about volts is that power in watts, as we mentioned earlier, is volts RMS squared over R. And in most RF systems, not all, some of them are 75, but the vast majority of RF systems nowadays are indeed 50 ohms for what we've got. Okay, so now we've got, let's do some substitution. We've substituted the power for volts RMS squared. We leave that plus 30 on the other side. And something that we know about volts RMS is that it's functionally equivalent to volts peak over square root of 2. And that's a very, very important distinction. This is where a lot of people get messed up along the way, as they kind of confuse themselves in terms of what's important. And they say volts peak to RMS. And this is something, once we get to the simplified equation, you won't have to worry about this anymore. But this is a pretty important distinction. Because now what ends up happening is we start breaking this equation down. We have our 1/50th. We've got our transformed this equation into this equation, and now we start pulling out more things. This square root of 2 squared gets pulled out to be 1/2. We've got our 1/50th. Of course, you multiply those two things together, and it's 1/100th. And of course, that reciprocal turns into the negative 100. So now we've got pretty much 10 log volts peak squared. Now, just simply a matter of minus 10 log 100 plus 30. This transforms into the 20. Of course, the 30 comes along for the ride. The square comes out and multiplies by the 10. And now we have 20 log V peak minus 20 plus 30, which of course simplifies down into 20 log V peak plus 10. It's an extremely simple equation that now we've got that you can pretty much just take to the bank. Anytime that you have volts peak of a carrier, you can say basically 20 log that value plus 10 is its power in dBm, of course, in a 50 ohm system. And that's it. I mean, life gets very, very easy and you're no longer dealing with I and Q separately, trying to square and square root. You just take that value of peak, 20 log times that value plus 10. That's it. Now, there's a question of your language of choice. What tools does it give you? Because basically, when you get that complex data set, what happens with that complex data set? What is it actually represented as? Well, in some languages, in some domains, in some drivers, they give you an array of I and Q, and you've got to figure out what to do with it. Now, that's just good old, square root of I and Q squared, add together, square root. But that math it's done all the time. It's easy to mess up. And one of the things that's particularly nice is that we're going to go ahead and show that within basically the LabVIEWs, inside of LabVIEWs domain, we're going to go ahead and just very simply use this transform that we have here that's available within the complex math palette. And it takes a complex value. And in this case, we just have a value of 1 at 0 degrees. And this is just kind of simulating what would be coming out of, we can kind of almost ignore that this is even here. Really what matters is we have a complex value at that point. And then we can go ahead and transform that, very simply get the magnitude out of it, 20 log x, and we get power in dBm. Now, if we were to go through and do the math on this one, you'll see that we have our power value here. If we had if we had a volts peak of 1, so basically 2 volts peak to peak, it would give you a dBm of 10. Now, one of the things that we saw on our oscilloscope is we had a value of 0.32, not 0.32, 0.32, 320 millivolts, just about on that. And this should correspond to a value over here of approximately 0. Now, the reality is I think it was like 3.17, and you'll see we're going to get a lot closer to that actual value of 0 dBm with a very, very, very simple transform of just getting the magnitude 20 log x plus 10 using an expression node. You could use the discrete math palettes inside of LabVIEW with the multiplies and the adds, and then also the mathematic and the logarithmic. You can, the exponential or, trigonometric functions. You can do those transforms if you desire. For me, life gets a lot easier just by doing this. Also, another tactic you could even use is the absolute value. If you take the absolute value of the actual complex value, it does the exact same transform up underneath the hood in a very, very clean manner. You can see we got that same power value down here, hopefully. And that's so key. That's such an important distinction because so many people get caught up on very, very large diagrams of breaking out real and imaginary and figuring out what to do in the transforms, when really, heck, you don't even need the complex palette. You just do an absolute value. This gets you volts peak, 20 log x plus 10, and you've got your power without any muss, without any fuss. Now, in particular, there's a pretty interesting way of actually viewing that relationship between the carrier and that complex value. And in fact, what I'm showing here is actually just a very simple simulator that's showing, now in this case, it's a complex, basically it's a complex carrier, but in general, you can see how the magnitude is changing, and then I can change the phase. And basically it's this magnitude and phase relationship, and it is describing what the carrier is doing. And that's basically all that there is in terms of the understanding. If you had basically something that was moving around and had a very crazy constellation, basically it's describing the complex value over time. And what would end up happening is, you'd have the carrier changing its characteristic amplitude and phase versus time. And that's really all that data is. So I hope this helped clarify a little bit. In particular, what does a carrier actually look like that's coming out of say an RF generator? Just like a sine wave. There's nothing too crazy. We know that we can look at that information. We can get a couple different pieces of information out of it. Of course, if we're trying to get power out of it, we need to know the magnitude of that carrier itself. And of course, we're going to look at it in terms of volts. You could either look at it in terms of volts peak to peak, volts RMS, or volts peak. Now, it happens to be a lot of RF instrumentation when it serves up a complex value that's describing the magnitude and phase of that carrier at a moment in time, that it serves it up in terms of volts peak. And we had gone through the math to actually show that simple equation going from power, working our way all the way down through volts RMS to volts peak, to a very simple equation that shows that it's just 20 log of volts peak plus 10. And then you'll get your power in dBm, once again, presuming a 50 ohm system, out of it. So hopefully this, next time that you're presented with a complex data set and you're trying to understand that data set more, just go ahead, don't treat it as INQ. Treat it as magnitude and phase. Just get that magnitude out of it, 20 log x plus 10 on the magnitude of that complex data, and you've got your power in dBm, which should get you pretty far. Thank you very much, and I hope to see you in the next lessons.